Okay, I think we've just hit 1:15, so we'll go ahead and start the session. So good day to everyone. Thanks for joining us. My name's Joshua Locke. I am a software engineer at VMware working in the Open Source Technology Center. With me today is Marina Moore, who is a PhD student at NYU in the Secure Systems Lab. And we were supposed to be joined by Trishank Karthik Kupusamy, but unfortunately he wasn't able to make it today, so I will be trying to present his content with less of the charm and wit, but hopefully as much of the accuracy. So what are we here to talk about today? We're here to talk about securing content repositories with TUF, or package repositories as the slide title says. So what is the problem that we're trying to solve here? Part of the problem is that our computers are pulling content from a variety of sources. They're usually doing that in a semi-automated fashion with little to no user interaction. So as software engineers, as developers, we have our operating systems, app store, dev tooling, probably one or more package manager ecosystems. For reusable components, we'll have containers, configuration management, and all sorts going on in our machine that's all trying to pull content from remote repositories and keep it up to date. And the state-of-the-art way to get that content into those repositories is to use a robot. So we like to have robots do boring, automated, repetitive tasks, and we entrust those robots to do much of our content publishing. And this is really a good thing. Robots will retrieve a key from a storage system, sign a release, and publish that release to a content repository with little to no human interaction in the best case. And this is brilliant. It gives us a single auditable point of contact for understanding what's happened in a system, and it removes the majority of human error. But the state of the art today is really still not good enough. We've developed this trend of DevOps, and what we really need is to insert some security in there and have DevSecOps. So we know that malicious parties can insert themselves into this process, and even non-malicious parties, but accidents happen. Developer error is well understood to be a problem. So what do we do when something goes wrong with this automation? And of course, the situation is much worse for non-state-of-the-art systems. It's easy to forget, but especially as open source folks, we can forget that there's a lot of systems out there that are using software engineering practices from a long time ago. So just how real is this problem? And what exactly are some of these problems? The previous slide had an ominous-looking figure in the background, but what are the sort of things that can go wrong? Well, of course, we've got some horror stories just to make sure that everyone is as frightened about this as we are before we start to talk about how we propose to solve the problem. So the first scary story is that in 2012, there was a piece of malware called Flame, and this was a very sophisticated piece of malware. It was able to avoid detection for a long time, partly because it was fairly targeted, but partly because it had done a lot of clever things. One of which was that the malicious programs in question were signed by certificates which made them appear to originate from Microsoft. This is a good way to avoid detection by appearing to be software written by the operating system vendor. And they done a bunch of clever legwork to understand how to appear to be from Microsoft, even though clearly this software was not developed by Microsoft. So they had found that a piece of Microsoft software, the terminal server software, had a licensing mechanism which would issue a certificate to say, this entity is able to use this software. And this certificate issuing mechanism was erroneously granting code signing privileges as well as the usual privileges to indicate that a license was granted. And so the attackers leveraged this and a very novel, what is called a collision attack. And this is a type of attack against a hashing algorithm, which where you feed it some different input and generate the same output. And the hashing algorithm in question, MD5, was theoretically susceptible to this at the time, but this was a very prominent example of this technique being used in practice. And they were able to use this collision attack to manipulate the certificates, to prolong the life cycle and to increase the places that this could be used to make it much more useful for the malware authors. And then the other clever thing they did is that they used this certificate to perform, and some other techniques to perform a man-in-the-middle attack against the Windows update system itself. So you had software signed by Microsoft being, or appearing to be signed by Microsoft, being shared by Microsoft's update mechanism, and that's how this software propagated amongst other systems. So it's a really clever, sophisticated attack. What lessons do you think we might take away from this? Well, for me, the big ones are that managing security keys is actually quite difficult, even for experts, and mistakes happen, and we need to have a plan for dealing with these kinds of mistakes. So our next scary story is to talk about Ccleaner. This is a utility for cleaning up Windows systems. And in 2018, so a few years later, it was discovered to have a backdoor. And somewhere in the order of 2.2 million downloads of this corrupted version were distributed. And a relatively small number of those, 1.65 million, phoned home. So this malicious software installed on users' computers was connecting to a server on the internet. But there was clearly some kind of algorithm going on for it to decide whether to connect back to its what we call command and control server. And then of those 1.65 million that phoned home, only 40 of those were targeted with a second stage attack. So the way modern malware is developed is that it effectively has an extensibility mechanism built in. So it can reach out to a command and control server to determine whether it should take any actions. And it can also download updates and extend kind of plugins to extend the features of the thing. And so 40 of those 1.65 million that phoned home were targeted with a second stage. And this resulted in around 11 kind of high-tech IT companies being infiltrated. And that's really significant. That was a highly targeted attack with quite significant targets. And the way they got into the Ccleaner systems is that there were some leaked credentials that enabled the malicious party to access some remote desktop software on their build infrastructure. And then they were really clever about it. They only used this remote access outside of the core working hours of the company that developed the software, so they were less likely to be detected. And they were able to propagate their attack and generate this highly targeted attack, which was quite successful. So what lessons can we take away from that one? Well, I think a really important lesson is that in software security, we continually are kind of flummoxed by the fact that an attacker really only needs to find one flaw, and we have to be able to defend against multiple. So in this instance, some leaked credentials and a publicly visible remote desktop system were all it took. And of course, it gets a little bit worse because it leads on to scary story number 3. In 2019, one of the world's largest computer makers unwittingly installed malicious software on thousands of its customers' computers. And it's highly suspected that the original compromise of ASUS was through the Ccleaner attack. The Ccleaner attack poisoned the well, and it enabled a very patient and sophisticated attacker to do some more damage. So 500,000 ASUS systems were compromised, 600 of those were targeted. So another kind of fairly targeted attack. One of the interesting things about this attack is that the malicious file that was delivered was signed with a legitimate ASUS certificate. It was delivered from an official ASUS update server. So it had all the appearances of an authentic piece of software. Exactly how the malicious certificate was attained is not certain, although the Ccleaner kind of attack is expected to be how they got their foot in the door, so to say. But one of the problems I soon run into is that this certificate was used to sign a lot of legitimate files. And when I say a lot, there were on the order of about 3,000 files that were, or 3,000 things were signed with this certificate. So it was a really difficult situation to recover from. If they just revoked that certificate, there are 3,000 things that their customers are using that are suddenly invalidated by this certificate revocation. So what lessons can we take away from this one? Well, I think clearly we learned that it's not enough just to sign software. And we also learn again that key management's really hard. And then scary story number 4, I'm not going to go into too much detail on. It's a very recent one. It was even more sophisticated than the previous 3. And it wouldn't strictly be solved by TUF alone, which is why I'm not going to go into too much detail. But I think it indicates that these types of attack continue to happen, and these sophisticated attackers continue to find effectively the gaps in the fence. So when we start talking about signing software and securing content repositories and things, we often hear people say, well, why not just use TLS, or why not just use GPG to sign a thing? TLS is a fine protocol that enables secure communication between 2 devices. It's the little padlock on your browser when you're navigating the majority of the web nowadays. There's been a real kind of uptick in secure traffic. But TLS keys are stored in effectively on the server, on one of the devices doing the communication, in memory, and they sign automatically to when the communication is initiated. And this is good, but it's not going to stop a serious attacker. It's kind of analogous to placing your key under the doormat. You've got the lock there, but finding the key to get in is fairly easy if you're knowledgeable or have time. GPG has its own set of problems, one of which is that it's really difficult to use. And one of the things I've started referring to GPG as kind of a security toolbox. There's a bunch of tools there, but you still need to understand how those tools interplay and how to build a secure system with those tools. So it's not enough just to sign some content with GPG. You need to think about, how do I securely distribute my GPG key? Anyone who's fairly involved in open source probably knows about the web of trust, and there's been, particularly over the COVID period, there's been a bunch of questions about how effective that system really is. You also need to be able to revoke keys, define trusted keys for your system. And even if you get all of that right, simple signing of artifacts provides you some security properties, but probably doesn't provide enough. So what lesson can we learn from all of these horror stories? Well, TUF has a really great security principle, which is compromise resilience. And this really is about 2 things which are indicated by this image. It's about making ourselves a harder target. So this is the notion of defense in depth. And as you can see, this castle's got a moat around the edge, and it's actually got a castle around the edge as well. So you can hide in your big castle on the inside, and you can defend the exterior castle with your sophisticated weaponry. And someone who's trying to attack you in this castle, they have to breach 3 defenses before they can do anything. So the other important lesson, I think, from the horror stories is that we need to acknowledge that we cannot prevent a compromise. We need to be able to mitigate the impact of a compromise. So effectively, we need to have a plan, a mechanism for recovering from a compromise. And to make these horror stories and my kind of lessons more concrete, I'm going to hand over to my colleague Marina, who's going to talk to us about the solution.
Great, thank you. So yeah, now that we know that this is a big problem, what do we all do about it? So if you go to the next slide. So I'm going to talk today about the update framework, or TUF, which is a framework for secure software updates that we both work on, that was really designed with this compromise resilience in mind. It really focuses on key management and revocation as kind of first-class principles of the system in order to make sure that they are designed in from the beginning, and it makes it as easy to use as possible while also providing all of these security principles. And so I think I'll start by going into some of the principles behind TUF and kind of its philosophy around how to secure these software distribution systems. So if you go to the next slide. The first principle is this idea of a separation of responsibilities. As all the examples that Joshua went over really illustrate, if you only have a single source of truth, a single source of information, that can be compromised. And if that happens, then your whole system is compromised. So instead, what TUF focuses on is this idea of separating the different responsibilities into different people, to different computers, to different keys, so that the compromise of any one of these things doesn't compromise the whole system, and each person is only responsible for their subset of the system. And so if you go to the next slide, the big way that this works in TUF is through the use of 4 main roles. The root role is kind of the root of trust for the whole system. This is the the most important, most secure piece of the system, and it's where this is the one thing you have to actually establish trust in, and then from there you can chain trust and kind of bootstrap the trust for the rest of the system. The next role is the timestamp role, which provides a notion of timeliness. And this notion of timeliness is really important when you look at key revocation and timeliness of information, because the state of the repository today might not be the same state that it has tomorrow. And if a compromise is discovered today, or tomorrow or whatever, you want to make sure that the signature of today is no longer valid, and then the users can detect kind of that change in the state. The snapshot role has kind of a similar idea, the idea of consistency, to make sure that you see all of the packages that are currently valid in a consistent state. And finally, the targets role is what provides the actual content integrity. This is very similar to like the actual signature on the package, which provides information about like the secure hash or of the content itself and other information. And this is the targets using the idea of separation of responsibilities. It's actually not just one entity, it's actually split into many different entities, each of which sign the packages that they're responsible for. So for example, if you're Microsoft, you might have one target's responsible for like the Microsoft Office suite and another responsible for like the Windows team, but these would be separate entities just trusted for their own subset of the system. So the next principle, if you go to the next slide, is the idea of threshold signatures. So even within each of these separated roles and responsibilities, there are cases when you'll want more than one set of verification on these files. This is especially important for things like the root role, which is a really kind of security sensitive role where you really want to make sure that it is well protected. And so this is done using threshold signatures. And the idea here is that basically you have to have 2 different people in 2 different, 2 different cities, 2 different continents, both sign the same piece of metadata to provide the double security. And this is really similar to, the idea in like, those nuclear bunkers where you had the 2 different keys that were more than arm's width apart, as illustrated here. So you require 2 people or a very clever one person with a long stick to churn both of them. So if you go to the next slide, our next principle is minimizing risk with offline keys. This really goes back to the idea that like in TLS, when the keys are stored on servers, the keys are only as protected as the server that they're stored on. And so what we allow in TUF and what we encourage is for people to store their more security sensitive keys offline. And the idea is that it's on some device like a YubiKey or some other external device, and then that's never on the internet, can be stored in a safety deposit box. And an attacker wouldn't be able to get to that key without some actual, like, physically finding this device with the key on it, which then makes it a lot harder for them to infiltrate your system from afar. If you go to the next slide. The final principle is this idea of delegations. This is kind of how that separations of responsibilities is put together. The idea is that instead of saying, okay, this is a signing key that you can use for any package ever, you say this is a signing key that should be used for this particular package and this particular set of packages that you actually have control over and should be responsible for signing. And the idea of this kind of tree of delegations that you can set up using TUF is that any one leaf of that tree, any one person with a key, if that key happens to be compromised, then only the things that they're responsible for signing are compromised, and that can't be used to kind of extend into an attack on any package that you might install. And so it really kind of narrows the scope of any compromise, going back to that idea of compromise resilience. All right, so if you go to the next slide, how do we put this all together? How does it actually work? So we use all these principles to design kind of basically a set of steps and principles to use in order to secure a distribution system, a framework as we call it, which kind of describes how you can use these principles in practice to make sure that all of these things work together. And there's also this focus on invisible usability. So with all of these principles, with all of these things happening behind the scenes, it can be a little bit complicated to get all the steps that happen. But the beautiful thing about code is that we can write that code once, and then people just have to run it, and they don't have to understand every single detail of what's happening unless something goes wrong. And if there's actually an attack and a malicious software or something like that, they might notice that there's a warning or that it won't install. But unless that happens, it just says, okay, you're verified, go ahead and install. And even on the developer side, it's mostly just running a script and uploading a signature to attach to this metadata, which is really as simple as possible with just a little bit of upfront configuration to decide those delegation trees and other kind of trust setup. For a lot more detail about how these things work and what the actual steps to take to put these all together, I would encourage anyone interested to look at our specification, which is linked here. And I'm happy to add that to chat or whatever as well. It goes into the actual step-by-step of these are the things that you must include in these different roles, in these different pieces. And this is the steps the client should do to actually verify all of those things that you do. Because having all this stuff on one end is only useful if it's actually verified on the other end. All right, so if you go to the next slide. Next, we're going to look at some cases where this has actually been used in practice and some kind of lessons learned there and what this means for everyone here. The first case study, which I'll go over, is Uptane. So if you go to the next slide, the modern automobile is, on the next slide, sorry, is a collection of a lot of different computers. It's actually everything from the radio to the engine to the airbags are actually controlled by these little computers. And computers mean software, which means that you'll want updates to this software if any bugs are discovered or anything like that. And so they require updates, and so they require some security. So what we've done, if you go to the next slide, is design a variant of TUF for automobiles, which is called Uptane because it has some slight differences from TUF, kind of unique to this automotive space. Because cars are very different than computers in certain ways, such as their ability for each computer on the car to access the actual internet and the network. So they have to do some kind of inter-vehicle communication. And they also don't have this sense of, because of the lack of network connections, they often don't have a good sense of a secure source of time. So they don't really know exactly, that idea of timeliness becomes a little bit trickier in this space. So after looking at all of those issues, if you go to the next slide, we have standardized Uptane into a IEEE ISTO standard, which is now in the Linux Foundation. And the version 1.1.0 was released at the beginning of this year. It was originally standardized sometime last year. And this is just kind of formalizing this idea of how you can use TUF in automobiles. If you go to the next slide, it's also, in addition to being standardized, it's been used in practice. Of course, it's been integrated into automotive grade Linux, which is the open source operating system and code for automotive ECUs. And I don't know if ECUs are just those little computers on cars. It stands for electronic control unit, just a small little computer. And it's been adopted as well by many major auto companies. And the statistic that we like to cite is that in the next few years, about a third of new cars on US roads will use Optane to some degree or another to secure some of those computing devices. All right, and then next slide, I think I'll pass it off to Joshua to talk about our next case study.
Yeah, so one place that we are actively integrating TUF today is the Python package index. And so this is a similar scenario to PHP repositories, and very near and dear to my heart because it's one of the things my team and I spend our time working on. And another reason I really like the PyPI case study is because it really demonstrates the flexibility of TUF, which enables kind of adoption in phases. So along with my own team, a lot of the work, particularly on the server side, is being done by Trail of Bits, under contract to the Python Software Foundation. So we've got really good kind of broad collaboration going on in the finest open source sense. And so here's a fairly, I guess, intimidating looking diagram, but one of the nice things about it is it demonstrates a bunch of the things happening in TUF that Marina talked about. So you can see that the green boxes represent offline keys, sorry. These are keys that are kept in a lockbox or a safe, or, generally not available on a computer. And they provide this extra level of security, and they kind of delegate authority to some online keys to perform some signing. And this is the phase we're implementing today, which is effectively trying to add what I call, or you might call, repository signing to PyPI. And what will happen here is that each time someone uploads a Python package to PyPI, it gets signed by the repository, and this gives some integrity protection against kind of malicious attacks, but also incomplete data and accidental kind of integrity errors. And what security promises this provides really is helps defending against man-in-the-middle attacks and what you might call malicious mirrors. So once this is deployed, you'll know that when you've downloaded a Python package, whether it was from PyPI directly or like a regional mirror or a corporate mirror or something, it was the same package that the upstream package repository had originally signed. It also adds a bunch of nice security features that we talked about, like not having a single point of failure, providing that compromise resilience that TUF is a core property of TUF. This deployment demonstrates the delegation model in practice. One of the interesting things about it here is that it's less about providing additional security properties, and the delegations are effectively a performance mechanism. PyPI has tens of thousands of software packages on, and so if we had a single metadata file listing tens of thousands of packages and that got updated every time more packages were added, that would be fairly laborious to download each time the repository state changed. So this bins to numbered bins delegation that you can see at the bottom of the diagram here enables fewer files to be downloaded, and the files are updated less frequently. So that's kind of a nice demonstration of some of the versatility of TUF, I think, that it can scale well and it can be deployed in kind of phases. And I speak about phases because what we're hoping to do next is implement the so-called maximum security model. So both of these PyPI designs are available on the internet as PEPs, so Python enhancement proposals. There's PEP 458, which is the previous slide I talked about. And then there's PEP 480, which is what we hope to work on next with this slide. And we're this extends the security by allowing a developer to choose to sign for their own packages using the delegation model. And then you know that what you have kind of downloaded and installed is what the developer originally intended to publish. So it reduces the trust on the repository. And some of the resistance to this kind of system is that managing signing keys, we've already said that kind of can be quite difficult, and a lot of open source developers are not interested in doing that. They just want to write their software and share it. But Trishank did some interesting research that indicated, using numbers from around 2016, that if we could encourage the top 1% of packages to be signed, that would account for 73% of the downloads on PyPI. So you can see that with we'd have to convince relatively few developers to sign their package, and that would be a significant security lift for the system. You can also see in this slide more of the delegation techniques that Marina already talked about. The claimed and recently claimed delegations are actually providing some security properties. What's happening there is that when someone originally signs and uploads their package, it's kind of, that delegation is done through an online key. And this is mainly to prevent some kind of operator having to frequently sign every time a new delegation happens. Going and getting the offline key out of the safe deposit box, plugging it into the system, and kind of signing that delegation. Instead, this phase is things. So your original delegation can be signed for by an online key, and then periodically, say once a month, an operator can come along and authorize a bunch of delegations with an offline key, increase that security, that protection by being protected by an offline key without making too significant overhead for the people operating the infrastructure. So that's kind of a high-level overview, like a scatterbrained overview of the PyPI model. This is actively being developed, worked on today, and because the Python enhancement proposals are publicly available, it also provides a really nice kind of demonstration of how to deploy TUF in practice, how to integrate it into other systems. And then for our final case study, I'll hand back to Marina, who's going to talk a bit about Datadog.
All right, so yeah, I'll talk about next how TUF has been integrated into the Datadog core integrations for use in secure software updates. And kind of the big thing I want to highlight here is the way TUF can be integrated with Intodo, which is another system from kind of a broader supply chain security model. So TUF focuses on this secure distribution aspect of the supply chain, but there's also, it's code signing and CI/CD systems and all these other pieces of the pipeline that I'm sure you're aware of. And Intodo is one of the methods to help secure all of these other pieces. And so this is the way that Datadog uses TUF as well as TUF to kind of distribute that Intodo metadata to provide end-to-end developer signing. So the code that's written by the developer can be verified every step of the way by the person who then downloads that software, which is just a very cool end-to-end model for supply chain security. And if you go to the next slide, there's a diagram of kind of how this all fits together. And you'll recognize some of these roles from TUF that we've talked about, and kind of a similar delegation pattern to the one we saw for PyPI, with the addition of kind of this Intodo metadata, which then provides that additional piece of securing the entire supply chain and providing attestations about everything that happened from when the developer wrote the code all the way to when it was actually packaged and released to you as the downloader user of this code. Yeah, and it does this through the use of delegations, again, to all these different roles, a variety of different targets roles for these different wheels, which is just the different packages as well. And there's a lot more information. Trishank wrote a great blog post about this integration. It's available at this link, which can provide a lot more information. It's just kind of a high-level overview of how this all works. So it's that. You have the next slide. think we have a couple minutes left, so I'll quickly go over some conclusions, and we should have time for questions. So if you, oh, and by the way, if you haven't yet, feel free to post any questions in the Q&A as I go over the next couple of slides. If you go to the next slide, is just very quickly, I'd like to acknowledge all of the wonderful people who make this work. As with any project, we didn't do all this ourselves. There are a lot of wonderful people behind the scenes in all of these different communities making it happen, especially our TUF maintainers and all the people in the Python and Uptane communities that really make this work happen on the day-to-day basis. So thank you to everyone here and everyone who I didn't have room for on the slide as well. And then if you go to the next slide, we have time for some questions. So feel free to ask us anything or email us if you have any questions as well. There's also various other ways to find us. There's our TUF website. We're available on the Cloud Native Slack, because TUF is a graduated project actually of the CNCF. And so we are available kind of on those ecosystems as well. And also, if you're really interested in this topic, I'd encourage you to attend another talk later today about kind of a project to integrate TUF into Drupal projects. So that is another exciting thing to look into if you're interested. Yeah, so then I'll flip over to the Q&A and see what we have there. All right, I'll just go in time order, I guess. Can you use this to sign and later validate your final build artifacts as well, or just individual packages that are hosted externally? Yes, I think you can use it. You can use it internally as well. You just run the same thing kind of on your local build artifacts. And in fact, we actually have a whole system in place to make sure that you download the correct packages from the correct external repositories if you're using more than one repository. Because I'm sure some of you heard of like the dependency confusion. So we really focus on making sure that you download the correct packages from the correct locations to prevent any of that kind of confusion. Feel free to jump in, Joshua, at any time as well.
I'll tell you that. Will TUF be used in voting systems anytime soon? I don't know. I'm not entirely certain I mean, I'm kind of skeptical of digital voting systems anyway, so I guess I'm probably maybe not the best person to answer this question, but one of the reasons I did want to jump in here is somewhat related to voting is kind of legal documents like city statutes and things like that, where you kind of want to know that you're referring to the latest version of that document when you are referring to it, and you want to know that it hasn't been tampered with when you're referring to it. And so there's a project called the Open Law Library, which is using TUF to effectively provide a content repository of legal documents and have the protections that TUF offers of, integrity protection and consistency and freshness. So that's it doesn't directly answer your question, but I think it shows that TUF is pretty versatile, which is why I tend to say TUF's for protecting content repositories rather than, it's named the update framework. It was designed for protecting software update systems, but it is demonstrated that it is more versatile than just that. So hopefully, yeah, not a direct answer of your question, but an interesting anecdote anyway.
All right, so the next one we have is, what is the relationship between TUF and Intodo? Will we still be vulnerable to supply chain attacks if we implement TUF without Intodo? So yes and no. So there are a lot of different pieces to the software supply chain. TUF really focuses on that distribution piece. And so on its own, if say your code repository, for example, is compromised, and then is properly signed and uploaded using TUF, TUF on its own won't detect that your code repository was compromised. So you'll need, other things to those other pieces of the supply chain. And what Intodo really focuses on is kind of linking all those pieces of your supply chain security together to make sure that you're actually doing all of these different pieces. Yeah,
so the relationship is effectively that their sister projects both came from the Secure Systems Lab at NYU, and they share some effectively like an envelope format for providing metadata that is signed, which is a separate kind of track of development now, but they share a lot of the same ideas and principles. And one of our co-maintainers on TUF has referred to TUF as kind of protecting the edge of the supply chain graph, which I think is quite nice. So if someone gets in and compromises, Marina indicated, if someone gets in earlier in the supply chain and compromises things, you can still end up with a package that is signed and appears to be legitimate. So the combination of the two, as Datadog did and talked about in Trishack's blog post, is a very powerful combination, actually.
All right, and then the next one, this one's really interesting. Does the TUF system create an opportunity for malicious actors to wait for an opportunity when an update is critical and intentionally poison the process, like a denial of service for critical updates? So denial of service attacks aren't like directly covered by TUF, because without control of the entire network, it's hard to actually prevent, any denial of service. But what TUF does do is provide kind of like it can detect the denial of service attack. And so it makes sure that if you're not seeing the latest information available on the repository, you will know about it. And it also specifically protects against things like freeze attacks, which make it so that you don't see the most up-to-date version of a particular package that might have a vulnerability that was just discovered. I hope that answered that question. Is there a quick start guide for on how on-the-ground developers can use TUF? So I think there's kind of two answers here. The TUF specification, I think, has a lot of the details of this, but I would also encourage anyone interested to read the PEP 458 and PEP 480s guides, because I think they have a lot more detail about some of the design decisions and other pieces that were used by PyPI when implementing TUF, which I think could be really useful, at least as a reference when doing this elsewhere. I don't know if you have any other good quick start suggestions.
Yeah, we do have, if you are relatively comfortable with Python, so we have a reference implementation of TUF, which is effectively, we don't make changes to the specification without having some confidence that they're like reasonable to implement. And so the reference implementation provides kind of both an example of how to implement TUF, but also has a symbiotic relationship with the specification. And in the reference implementation, we have a quick start, which uses some simple command line wrappers for the reference implementation to kind of instantiate a repository and fetch some file from that repository. And then there's also a tutorial that goes through some of the reference implementation kind of library functions and shows you how to use the Python to generate the metadata and fetch it. And so that's very hands-on, obviously, and gives you a good idea of what the metadata looks like, at least JSON formatted metadata looks like in practice. And yeah, so I think that's a fairly good place to get started.
Yeah, definitely. All right, so considering the Drupal automatic updates use case in particular, will it be enough to implement TUF but not in toto? What kinds of vulnerabilities would we be subject to if we do TUF only? So I think the tricky thing about security is I don't think any single thing is ever really enough when it comes to the security of your system. I do for sure, I work on this project. I really think that TUF will help with a lot of the more common situations. That being said, I think anything that happens kind of before the distribution and packaging isn't actually covered by TUF. And so you have to do other things as well as this to make sure that the whole system is secure. But I guess you could do that vetting yourself as a developer who does the packaging of software if you want to do it manually.
Yeah, that's right. So you get, if you have TUF but not in toto, then you know that the update you downloaded is what the author or repository intended to publish, and you have a reasonable amount of, or you have fairly good confidence that it hasn't been tampered with and that it is the latest version available. But you you can't know through TUF alone that, for example, one of your contributors didn't integrate some malicious, or their account wasn't used to integrate some kind of malicious change. So Intoto can provide additional security properties. You can do things like require that all of your developers are signing their commits, and that those commit signatures are verified by a system that kind of then signs an additional piece of metadata to say, yes, well, all of the commits were signed by authors that we trust. And so, it all layers up the security, the defense in depth principles. More like a security onion than the kind of concentric castles with moats once you start adding a bunch of policies with Intoto. And then we have another question. I think we're still good for a few minutes. How does TUF interact with the idea or project of reproducible builds, if at all? Not a huge amount, actually. I mean, reproducible builds are an amazing thing for security, particularly in open source software. From an update system perspective, I have seen people do clever things like we know our software is kind of binary reproducible, so we can. There's a Linux distribution called ClearLinux, and they do binary diffing of their updates because they're kind of binary reproducible builds, so they can just when the binary changes, that is effectively the updates, right? So they can do really efficient updates through binary diffing. But that's not really interacting with TUF at all. There are some collaborations between the Reproducible Builds project and the Intoto project, and you can find, for example, the Debian project, who really behind a lot of the Reproducible Builds work, are looking at using Intoto to add some verification on top of reproducible builds. So you can do things like say, Debian package is reproducible. We'll build it on X different systems. So each of those will sign a little bit of Intoto link metadata. And then when the user installs this Debian package, they can see that it was the same contents were reproduced by 3 different rebuilders with this Intoto link metadata, and have a strong level of confidence that the thing they've installed hasn't been tampered with. I couldn't tell you exactly any links off the top of my head, but you'll definitely find some information about that on the net as well. CubesOS, which is a very security conscious Linux-based operating system, they have been playing around with Intoto a bit recently as well. So yeah, there's definitely some not even overlap, but some synergy, I guess, between these projects and their ideals, but no direct interaction, I think, between TUF and the reproducible builds work.
Yeah, I think they're more like just, different stages of the same pipeline. So you should do both. the short answer.
Yeah, more security is more better.
Yep.
Okay. I think we're out of questions.
Yep.
So we are a few minutes early, but I won't keep you unnecessarily if there aren't any more questions. We'll thank you very much for your attention and your interest in TUF. And yeah, I'm really looking forward to seeing Drupal in TUF. And so definitely recommend you check out the Automatic Updates Initiative talk, which is happening real soon now, I think.
In like an hour. Yeah. If I converted
that. Yeah. Alrighty. Thank you very much.
Thank you, everyone.
Have a good conference.